I'm very happy to have in this session Dimitrios Giannakis, who has done his undergraduate studies in Cambridge. Then he continued on and he did his PhD, I believe, with Andrew Maida.
I was a postdoc with Andrew.
A postdoc with Andrew Maida.
Yeah.
You were in Chicago,
For
where
PhD.
you did your PhD. He did his postdoc with Andrew Maida, and then he stayed on the faculty of the Hellenic Institute for several years. Before recently moving to Dartmouth. Dimitrios done exciting foundational work in AI for science, and so he has also been the recipient of several awards. One of the most prestigious ones, it's only 5 or 6 per year that are given out, is the Vannevar Bush Fellowship. He has been a recipient, and Dimitri, we are very much looking forward to your talk.
Thank you very much, Petro. Hi, everyone. And thanks to all the organizers for organizing this very exciting event and for giving me the opportunity to present. So I will talk about work that we've been doing over the past few years on using ideas from quantum theory and data science for basically modeling classical dynamical systems. So this is work in collaboration with colleagues, students, and postdocs, and I will acknowledge them as the presentation moves along. So to start, I'd like to show an excerpt from a paper of Feynman from the 1980s, which in some aspects ushered in the field of quantum computing. So in this paper, Feynman asked the question, what kind of computers should we be using to simulate physical systems? And his argument was that since nature is quantum mechanical, at least to the best of our knowledge, the computers that we use to simulate nature should also be quantum mechanical systems. And for instance, this could be used to address the exponential cost in complexity when one uses a classical computer to simulate a quantum many-body systems. And over the past few decades, there has been considerable interest and research in both on the theoretical and applied side on designing quantum algorithms. So the problem that I would like to talk about today is somewhat of the converse nature. Namely, I want to talk about ways that we can leverage ideas from quantum information science to simulate classical dynamical systems. So after all, classical physics governs a great deal of phenomena of interest, and if quantum mechanics can give us, if rather simulating a classical system by a quantum system is a quantum system by a classical system can be an exponentially hard problem, perhaps we can get exponential gains when we try to simulate a classical system by a quantum system. So this problem has been studied by various groups. This is just a sampling of the literature, and there has been techniques that use quantum algorithms to simulate systems, dynamical systems described by differential equations, both deterministic and stochastic, and also recently even turbulent fluid flows and partial differential equations. So I will be telling you about work that our group has been doing in this area, focusing on two aspects. On the one theme will be data simulation algorithms. I will explain what this is about, and also implementation of these algorithms in quantum circuits. So maybe I should ask how many people from the audience have at least some experience with quantum theory in the past. Okay, so some people. For those of you who haven't, fear not. I have here a one-slide crash course of what would normally be a one-semester course in a university that summarizes the main axioms of quantum theory that we'll be using today. So in a nutshell, you can think of quantum mechanics as a generalization of classical probability theory, where objects which in the classical world are represented by functions like random variables or probability densities. In the quantum world, we generalize this and we represent them by operators instead. So for a quantum system, the state is described by a so-called density operator. So what is a density operator? It's a linear operator that is acting on a Hilbert space. The particular Hilbert space will depend on the quantum system, and it has the properties that it is a positive operator, it has, and it has unit trace. And you can think this as an operator theoretic generalization of a probability density. So a probability density, as we all know, is a function that is integrable, positive, and its integral evaluates to 1. And you can see here the analogs with this notion of density operators. In quantum mechanics, observables are also operators. They are, in fact, self-adjoint operators on the Hilbert space. Think of this as some kind of generalization of a Hermitian matrix in finite dimensions. And in analogy, again, with classical statistics, we can think of observables there as random, like real-valued random variables, and the self-adjointness is the quantum analog of real-valuedness from the classical world. We can, just as in classical statistics, if we have a system which is in a given quantum state rho, we can compute the expectation of quantum observables using this formula here, which is some type of generalization of of the computation of a classical expectation by integration against a probability density. And we also have a recipe of computing probabilities of outcomes of events. So omega here could be, for instance, some interval that, and you're interested in computing the probability that measurement of a quantum observable when the system is in state rho would lead to a result in that interval. And this is done by the so-called spectral decomposition of the observable that you're measuring. In analogy, again, with classical statistics, you can think of this as being somewhat analogous to saying that if you want to compute the probability of an event, you can compute the expectation of the characteristic function representing that event. Dynamical evolution happens by means of unitary operators. These are infinite dimensional, potential infinite dimensional generalizations of, let's say, rotations that we would have in finite dimensions, so like unitary matrices that map quantum states to quantum states according to this formula here. They act by conjugation. And there is also an analog of Bayes' rule, where we can condition a quantum state by so-called quantum events. So in classical statistics, we can represent an event by its corresponding characteristic function. And what is the characteristic function? Is a function that takes values between 0 and 1. In quantum mechanics, we replace that function by an operator, E, that takes values between the 0 operator and the identity operator. This is known as a quantum effect. And there's a formula here that generalizes the Bayesian update rule in quantum mechanics. So our goal here is to basically, given a classical dynamical system, to encode it into a quantum mechanical system using this, this framework over here, which I will walk you through. So the approach that we're going to take to reach this goal basically builds, and we're really standing on the shoulders of giants here, on the framework of operator theoretic ergodic theory, which focuses on studying the evolution of observables under general nonlinear dynamics. So by dynamics here, I mean some map. This phi is the evolution map. T here denotes time that takes points in a state space. So these are states of the system into itself. And in general, this can be a highly nonlinear map. We can think, for instance, as like a fluid flow or some other chaotic dynamical systems. We saw some examples of fluids and gases earlier on today, so this would be an example of that. And by observables in this context, we mean things that we can measure about the state. So these will be functions of the state that take values in some other space Y, which we're going to take here to be either the real or complex number. And the key property here is that these spaces of observables are actually linear spaces, meaning you can add and scalar multiply together observables. We will focus on the induced action of this dynamical system on such spaces of observables. Well, it turns out that this action is basically described by linear operators. These are known as Koopman operators after Bernard Koopman, who was in the previous slide, who introduced this concept back in the 1930s. And basically, they act on observables by composition with the nonlinear evolution map. So even though this map phi t here can in general be highly nonlinear, the map that takes observables, an observable f, to a new observable, which is defined by composing f with phi t, is actually a linear operator that in some sense encodes the underlying dynamics. And this operator has a dual known as the transfer operator, which acts on the dual space. So the dual space for typical choices of f will be a space of measures like probability distributions. And it describes how a dynamical system acts on probability distribution. So it describes the evolutions of statistics under classical nonlinear dynamics. And the one nice feature of working in this framework that basically it allows us to use the full spectrum of technique from linear operator theory to study nonlinear dynamics. And there was no linearization done here. We were basically intrinsically representing a nonlinear evolution in a state space by linear evolution in a space of observables. In recent years, there has been quite a bit of interest in combining this framework with techniques from data science and machine learning to develop methodologies for spectral analysis and forecasting of observables of dynamical systems. But what I want to focus on here is the connections of this framework with quantum theory. Because as we will see in a moment, these types of operators are very closely related to these to the operators that are used in the mathematical formulation of quantum systems. And we can take this to our advantage to design quantum algorithms for classical dynamics. Okay, so this, I'm not going to go so much into the technical details. I'm happy to talk about this offline. This will be a high-level overview of our approach, where we're going to go through different levels of description of a given dynamical system. So at the classical level, we have a evolution from a state space into itself, as I was talking about earlier. So the first thing that we can do here is that we can create a copy, essentially, of this evolution into an evolution of probability measures. So this is like what I call here the classical statistical framework. This can be done in different ways. One way, for instance, is to map every point in the phase space X by a Dirac probability measure in the space of probability measures on X. And then we have the transfer operators that I introduced earlier before that maps probability measures to probability measures. And this mapping has the basic property that this diagram here commutes. So we have basically, essentially what we're doing, we're creating a copy of our original dynamics into this space of probability measures. So we have this space of classical evolution of statistical distributions. Now, this is, again, as I mentioned previously, there has been quite a lot of work on using transfer operators for modeling dynamical systems. But for us, this is only the starting point, because our main interest is actually to create a further embedding where we take now this classical statistical evolution and we embed it into a quantum mechanical evolution. So here Q of H represents the set of quantum states on some appropriately chosen Hilbert space. So these are these density operators. I will explain how we choose this Hilbert space in a few slides. And what we're after is we want to create a mapping that takes us into this space without any loss of information, and an evolution operator that makes now this diagram commute. So we're creating essentially a copy of our classical dynamical system into a much bigger space of quantum states. The idea here that this can actually be the starting point, not or a good starting point for creating quantum computational representations of the system. Because after all, a quantum computer is a finite dimensional quantum system with a very particular type of Hilbert space. I'm denoting here by B sub n. It's basically a Hilbert space that has a tensor product structure given by tensor products of individual qubit Hilbert spaces. So we want to create a mapping from projection now from this infinite dimensional space to a finite dimensional space and a corresponding evolution. This will be a quantum algorithm in effect that has the property that this diagram commutes ideally, and moreover that this evolution can be implemented using using basically a short running time, like a few quantum resources, like quantum gates. So the two aspects that I want to highlight in this approach is that by working on these spaces of basically operators, these non-commutative spaces of operators that are used in quantum mechanics, on the one hand, we are able to have favorable structure preservation properties. Even if we implement these algorithms classically, so on a classical computer, there can still already be some benefits. And also the approach is generally amenable to implementation on quantum computers. I will show some examples of that. Okay, so the first application is on data simulation. This is in collaboration with my PhD student David Freeman and Brian Mintz, who's another PhD student at Dartmouth, Abba Surmast, and Joanna Slawinska. So what is data simulation? Data simulation, in a nutshell, can be understood as some kind of sequential inference about the state of a dynamical system that is only partially observed. So imagine that we have an iterative prediction correction cycle where we have a probability distribution associated with the state of a dynamical system, and we have a dynamical model that pushes forward this distribution in time. This creates for us some type of prior distribution, and when we make an observation at a later time, we update this distribution using Bayes' rule to get a posterior, and we keep iterating this cycle. This is widely used in numerical models like in weather prediction or object tracking and many other applications. What we want to do is we want to take this picture and basically create a quantum version of it using basically the general framework I described. I will skip the technical details as I mentioned, but as in a nutshell, what we're doing, we're using the Koopman operator as the unitary evolution operator that we have for quantum mechanical systems. And we create a mapping where we take probability densities of the system. So this is what the object that data simulation deals with. And we map them into density matrices, which are so-called pure quantum state, if you have seen that terminology, which are basically rank 1 projection operators that project along the square root of a probability density. This would be called a wave function in quantum mechanics. And we have a representation of classical observables by multiplication operators on our Hilbert space. This is basically an algebra representation. I don't have the time to go into that, in a manner that basically makes predictions from the classical framework. So these are expectation values of observables evolved using the transfer operators with quantum mechanical expectation values using this unitary evolution operator here. So this is now creating an a copy of our system in an infinite dimensional quantum system, which we can now project to arrive into a computational algorithm that operates instead of density operators with density matrices by projecting onto finite dimensions. One of these advantages that this scheme has, even if we implement it on a classical computer, is that it's quite natural to preserve positivity of states and positivity of observables. This is basically taking advantage of the fact that if you take an operator, it's very easy to project project positive operators to positive operators by conjugations, whereas the same fact doesn't occur when you try to project functions. If you orthogonally project a positive function, the result need not be a positive function. There are things like Gibbs phenomenon and so on that can occur. So the take-home message is that using this infinite dimensional quantum system as a starting point to create computational algorithms can be beneficial because of enhanced positivity preservation properties that the spaces of operators give us. We have basically a way of creating a sequential update scheme that we can train using data, basically samples generated from our dynamical systems, where we use the transfer operator to push forward in time the density operator, which is basically how we encode our knowledge about the state of the underlying classical evolution that this is like a latent state that we're inferring. And there is something which I don't have time to talk about, we call it here a quantum feature map, that uses basically some operator-valued kernel approach to approximate the Bayesian update. So I'll show one example of this scheme using drawn from climate science. So basically forecasting the El Nino southern oscillation using data obtained from a climate model. So the El Nino phenomenon is an oscillation in the sea surface temperature in the tropical Pacific Ocean that occurs every 5 or so years. Now we're actually predicted to be in an El Nino year. You may have seen that in the news, which is characterized by anomalously warm waters in the equatorial Pacific Ocean, and that can affect weather patterns throughout the globe. So here what we did, we took basically a climate model, used a long simulation of the climate to provide training data to these algorithms, and then use that data to make predictions of the sea surface temperature in some portion of the Pacific Ocean. So this is like a proxy for El Nino. So this is just some highlights from these results. So these are running forecasts where the x-axis here denotes the verification time of the forecast. As we go down in the panels, it's the lead time, so how far in the future we are predicting. And basically, what I want to show from this is that we naturally get a representation of both the forecast mean and the forecast uncertainty. Basically, in these quantum states that we're using to represent the state of El Nino, we encode entire forecast distributions rather than, let's say, just the mean or variance. How much time do I have? About 5 minutes. Okay. So for the rest few minutes, I want to say a few words about now how we can go about to implement now this scheme. So this was, I should say, using purely classical computation. It was a quantum algorithm, but it was run on a classical computer. But now how we can use these, basically implement this idea on actual quantum computational hardware. So the focus here is now, before we were in this level here, the focus now is we want to create finite dimensional quantum systems where the Hilbert space has a very specific structure associated with an n-qubit quantum computer. So the potential computational advantages that we have here is that with n qubits, we have this tensor product Hilbert space, which has an exponentially large dimension in the number of qubits. And we want to basically create a projection map from our quantum system here to the quantum computer that leads to a corresponding projected evolution in this arrow here that can be implemented efficiently on a quantum using a shallow, basically, quantum circuit. So we have basically investigated this problem for a specific class of systems. These are so-called systems that have pure point spectrum, if you have seen this term from ergodic theory. These are basically highly structured systems where the Koopman operator is diagonalizable. It has trivial continuous spectrum. So in this type of situation, what we have been able to show is that there is a very nice factorization of, you can get to a projection of your the generator of the dynamics into a quantum mechanical generator that factorizes very nicely in this tensor product form that basically allows you to implement its corresponding unitary evolution operating in qubits in parallel without any communication between individual qubits. And that basically leads to a highly efficient quantum circuit implementation for this type of systems. I'll just show a very quick example. If you wanted, for instance, to predict a sine wave, like a simple harmonic oscillator using this approach, but what happens as you increase the number of qubits? So like n here is like 3 qubits. So the possible predictions that this system can make is 2 to the power n. So here we have basically 8 type of outcomes. So this grayscale here shows a probability distribution for what this system predicts for the sine wave. And you can see it's clearly quantized. After all, it's a quantum system of sorts. And then as we increase the number of qubits, this distribution very quickly concentrates around the truth. This is just a very simple example for intuition. So we have actually implemented this. I don't have time to describe. There are different steps that one has to implement, most notably the fact that when we make measurements from quantum computers, we cannot simply measure what we want, unlike classical computing. We can only measure very specific quantum observables, so we have to actually transform our system, our quantum state, in a basis where measuring from the quantum computer actually gives us prediction of what the observable of the underlying system that we actually care about to predict. And this approach has some nice advantages. In particular, I want to mention that using resources that are polynomial in the number of qubits, we can simulate classical spaces of observables which are exponentially large. I'll leave you maybe with this last slide. These are like some actual quantum computation experiments that my collaborators, Jörg Schumacher and his student Philipp Pfeffer, did on a quantum IBM system installed in Germany for this simple harmonic oscillator example. I mean, arguably this is a system that you could code in like one line of MATLAB code, but it took a lot of effort to actually get this to work on a real quantum computer, and we're excited about future possibilities. So maybe I'll stop here, and thank you very much.
Thank you very much. Are there any questions, please?
Thank you very much for the excellent talk. I would like to ask, is it possible to develop a method for data simulation using classical coarse-grained statistical mechanics instead of quantum statistical mechanics? I think, yeah, I don't see why not. I mean, I guess one thing I wanted to highlight with the quantum version of statistical mechanics is that it gives us a very natural way to get, I mean, I went through this pretty fast, this idea of positivity preservation. This happens almost automatically when you have like the quantum version of the algorithm, because basically if you take a positive operator and sandwich it from the left and right by projections, if you take a positive matrix, for instance, and compose it from the left and right with projections, you end up with a positive matrix. So you have like this structural preservation property. This system, if it's trained, let's say, with data like in weather or climate forecasting, like moisture, that has to be positive in order to be physically meaningful, it will only make positive predictions. So it has these extra structure preservation properties that I'm not saying that, of course, you cannot do that with classical methods, but you have to work a little bit harder for that. Here it happens basically automatically.
Is there another question? Giannakis?
Are there physical observables that are less easy, more easy? You said order n squared.
Yeah, so that's a great question. So one of the things that I should have left more time to talk about the future direction. One of the things that we are currently working on is to generalize these results for this circuit that is order n squared in depth.
which was designed for very structured systems. So these are these systems that have pure point spectrum of the Koopman operator, which basically leads the structured nature of the spectrum leads to a very efficient circuit representation. So if you have a more general system, like a mixing dynamical system, like Lorentz, chaotic system, the Koopman operator will have continuous spectrum, and that circuit that I described will not work out of the box. So now we're trying to think about ways of generalizing this construction to this more dynamically complex system, and see whether we can still get a quantum advantage. It's definitely a challenging problem.
Okay, let's please thank Dimitrios once again. Okay, our next speaker probably needs no introduction, but I will attempt one. This is Ioannis Kevrekidis.
We know each other over many years.
That's true. Ioannis Kevrekidis did his undergraduate degree at the National Technical University of Athens in chemical engineering. He continued with his PhD studies in Minnesota, and then after spending many years as a faculty at Princeton, he moved to Johns Hopkins University a few years ago. He's a person that has been distinguished by numerous prestigious awards. But besides the awards, I would like to say one thing. Everybody these days talks about machine learning and neural networks do this, and machine learning does that, and all sorts of things. Ioannis did all these things about 35 years ago, before computers were powerful to do any of the things that they do today.
So we can live with green.
It's a joint introduction here.
Yes. Basically, I used to be young and promising a long time ago. Thank you.
And you remain young and promising.
Okay. Actually, I was thinking about today. Thank you all guys for the organization. This takes a lot of work, and it's not obvious to us, the speakers. And B, it was a real pleasure to hear all of the talks, because I learned a lot, and I was noticing how young all of the people are, which is also wonderful. This is blue for me, but it's green here, and it's okay. And so as Petros said, I'm one of these engineers who always wanted to be mathematicians, but never became. What I will talk is about places where there is an interaction between machine learning and modeling, mathematical modeling. And for me, mathematical modeling is classical, ODEs, PDEs, stochastic differential equations. This obviously is work with many wonderful people over the years, including a whole bunch of Greek people, some of which are friends and collaborators and are here. And then also, maybe I would like to note Bill Gear, who is the Gear of Gears method, that we worked together for 20 years or so, and Rafi Koifman, who is a harmonic analyst, and we also have been working together for 20 years or so. So in multi-scale modeling, that is something that many of us, including Petros and me, are interested in. You have systems that are described at two different levels, maybe multiple different levels, but think of two. This is one of my favorite examples. There's a bunch of dots over here. These dots are supposed to be plankton microorganisms. What they do is that they give birth, they die, they evolve, they are swished around by the ocean. And what you see on the left is what the particles are doing. What you see on the right, and I didn't like me, and let me see if I can do it again. So let me see if I can stop it. What you see on the right is the macro observation, it's the pair correlation function, which tells you how many neighbors you have in a neighborhood on average. And this is a beautiful, nice function, maybe with a little noise, which is evolving in one-dimensional space. And if you can write an equation at the macro level, then all the tools that we have work, stability, fixed point algorithm, simulation, whatever. But this is something that you can mostly just run and look at. And so the idea is how to bridge micro with macro. Let me kind of mention for the people that talked about generative models. Here is a version of a generative model for us. Somebody gives you a pair correlation function. Can you make acceptable particle configurations that have this pair correlation function? This is a very difficult problem. Other such generative or lifting problems, as we call them, are much easier. And The point is, the way that this is typically done is that much smarter people than me usually have derived macroscopic equations under some assumptions for the macro observable. And the question is, how do we go from such a description to that description if we don't have these smart people that know, let's say, how to go from the Boltzmann equation to the Navier-Stokes? The first thing that we did a long time ago with Bill Gear is to go back and forth between the macroscopic equation that you don't know and the microscopic model that you presumably have. We call it equation 3, which is a misnomer, not because there were no equations, but the equations were at the micro level, at the particles, and we wanted to simulate at the macro level, at the pair correlation function level. The main idea, and the reason that I kept this slide, is that I wanted to, for a moment...
Can you stay closer to the microphone?
Close, yeah, thank you. So the point that I wanted to make is that if you think of a lot, so for me, algorithms is integrators, linear equation solvers, fixed point algorithms, eigensolvers, things like that, okay? Algorithms that have to do with solving physical, time-dependent, space-dependent models. An algorithm, if you really think about it, of the type I'm talking about, is really a protocol of where to do the next function and maybe Jacobian evaluation. So an algorithm is really a sort of adaptive data collection. So if you have a formula, then you know what the time derivative is. If you don't have a macroscopic equation, then you don't know what the time derivative is, which you need to integrate. So what you do is that you do a burst of micro simulation with particles, you observe it on macro observables, estimate the time derivative and take a macro step. The idea again is to go back and forth between the effective dynamics, as Petros also calls them, and the micro simulation, and to do just the right design of experiments. In this case, not to learn the effective dynamics, but to solve them without writing them down. So the idea is how to do, if you want, data-driven solutions of equations that you don't have written down in closed form. Equation 3 then kind of went to what we called variable free, that again everybody uses without necessarily calling it variable free. The idea is, in the previous problem, I told you that the right macro observable was the pair correlation function. But how do you know that it's the pair correlation function? Typically, we know the right observables either by taking a systematic hierarchy, so you have a cloud of points, you look at various moments of this cloud of points. Sometimes you either your brain knows or you are very capable mathematically, and you can go from, as I said, from the Boltzmann equation to the Navier-Stokes. And what has happened in many fronts over the last several years is that you go to the computer science department and use data mining, for example, manifold learning techniques or autoencoders. We use diffusion maps to go from actual simulation data at the micro level to macro observables. This was done maybe 130 years ago first, when people did principal components. If data live in a high-dimensional space, but really in a hyperplane, then we can describe them with a smaller number of observables. And then, and this is kind of cute, I think, I don't know if a chemical engineer, since I'm also a chemical engineer, a guy called Mark Kramer in 1991, a guy who was a professor at MIT and didn't get tenure. He has done fine in life after that. He published a paper that he called nonlinear principal components, and where he introduced, as far as I know, autoencoders. If you have a previous reference, please tell me, I'd like to know. So the idea is to go from high-dimensional data through an encoder to low-dimensional. If you train this and you learn the identity, then you're lucky, you can have a coarse-grained description of your microscopic high degree of freedom problem. I also am saying this because I wanted to say that in the olden days for me being early 90s, training something like this, you realize, is a nonlinear, non-convex optimization problem. It took forever, it would crash. You wouldn't know if it wouldn't work because it crashed, because you didn't have a good initialization, because the system is not really lower dimensional. A lot of these things have gone away today with better computers and more data. The other approach which we kind of tend to favor is to do a spectral approach to getting low-dimensional descriptors. Here you have this, it's called the Swiss roll. It's a 2D surface in 3D, and basically you can write an eigenproblem that would understand that it's two-dimensional, and that will give you a good set of coordinates on it. These coordinates are the right variables in terms of which to write your macro equations. And so here is some of the old stuff. I won't make you suffer too much with the old stuff, but it's kind of interesting. So this was the time after neural networks stopped being fashionable in the late 80s, and some modelers like us were still using them. This is a paper that has a weird title, Discrete versus Continuous Time Nonlinear Signal Processing of Copper Electrode Solution Data. It was based on experiments in the lab of Jack Hudson, and the basic idea, and the reason that I'm showing this to you, is because this is a place where some interesting architectures of neural networks naturally came up. So what is this example? Where is it coming from? There was lots of time series from dissolving a metal in an acid for various values of the potential between the metal and the reference electrode. And as you change that, you see the value 0.6703, 0.6768, you go from steady time series, or steady states, to oscillations, to messier oscillations, and messier oscillations, and messier oscillations. And down here you see that you, in phase space with time delay reconstructions, you have fixed points, limit cycles, period doubled limit cycles, period quadrupled limit cycles, and chaos. And the point is, how do you go from one time series and parameter values to a model and understand the bifurcations for it? This is why I'm showing this example. This is a Runge-Kutta, which is something that we all have been taught at some point in our numerical analysis class. And that is a neural network that is templated on a Runge-Kutta. Look at what the Runge-Kutta does. You take an initial condition y, you calculate f of y, you multiply this f of y with a small time step, you add it to y0 and calculate f again, you do it again and again, and then you do a linear combination of these intermediate stages. Out there, yn is the current data point, yn plus 1 is the next data point, and what you see is a recurrent network which is basically implementing exactly what you see in the Runge-Kutta. The 4 stages are exactly the same. You can call it recursive if you want. You do 4 times the same evaluation. And then at the top, you are learning the residual, that is the difference between yn and yn plus 1. By adding y0 every time, the Runge-Kutta is doing what recurrent nets are doing. That is, you don't have this problem of vanishing gradients. And basically what I want to say, and I'm going to say it here, and I'm going to say it in a couple of different places, I kind of have this religious belief that if you look carefully at architectures for neural networks that have come up on the, let's say, on the machine learning side, and you look at them carefully, you're going to recognize algorithms that you know and love. In this case, recurrent resonance are Runge-Kuttas. And this is the typical archetype for the resonance when they came up in 2015. If you look at it, you will realize that it's a forward Euler. It's kind of common knowledge. You take something, you take a function, multiply by a small number, and add. So a resonant, this simple resonant is a forward Euler. So what we did for the problem that I told you with data is that we took windows of the time series. We used autoencoders to find a good latent space in which to work. And then we used these Runge-Kutta templated recurrent resonance to learn the right-hand side of the equation. So this is not learning the solution operator. This is learning or approximating the right-hand side of the differential equation itself. And having the differential equation approximation, then we could do bifurcation diagrams, get attractors, and so on and so forth. And there were many other things that are architectures that are motivated by numerical analysis. For example, just look at the thing at the end. It is a neural network that is implicit. It requires solution of equations to evaluate it, and it comes from trying to implement a Crank-Nicolson, a trapezoidal rule. So again, there's many different types of architectures that map to, if you want, numerical analysis algorithms we know and love. Let me also say a word about error analysis. If we have a model, true ODE, and then we have the real solution and the numerical solution, the difference between the two is forward error analysis. There is 2 types of backward error analysis. One says, you see the MD, that's the modified differential equation. I have my problem. I find the numerical solution of my problem. What is an equation whose true solution passes from my numerics? That's typical backward error analysis. And then there is this kind of, this is a very bad name, inverse modified differential equations. This is what these neural network identification schemes do. You have an actual problem, and then you find an equation whose Runge-Kutta passes from the true solution. So there is a nice numerical analysis framework for analyzing how well you're doing. And we did this kind of thing also for spatially distributed systems. So this is what you see up there are snapshots of a movie that has to do with the catalytic converter. It's carbon monoxide oxidation on platinum. Each square is roughly 500 microns by 500 microns of a platinum catalyst in vacuum. Red is more oxygen, blue is carbon monoxide. As you go in time, these patterns change. You take the patterns, you find the right latent space. What's the right latent space? You do principal components, and you find that the movie can be reproduced in terms of 4 principal components. So then the movie becomes 4-time series, and then you use a neural network to learn the dynamics in these 4-time series, and you can run this in order to reconstruct the experimental attractors. Again, the point being here that ideas that come in signal processing and data mining themselves map a lot to algorithms that have to do with numerical analysis. And the last one thing from the past that I'm going to tell you about is not learning solution operators for problems, but learning the right-hand side of partial differential equations. And, you know, if you think of a parabolic partial differential equation, it's a relation between the time derivative and the function, a few spatial derivatives, and the parameters. So when you have data, every point in space-time in a solution movie for a PDE or in a spatiotemporal experiment gives you information from trying to approximate the right-hand side. And the idea, and again I'm showing this because I want to make a point, is that if you think of a finite difference stencil in one dimension, we take, let's say, 5 points, we estimate derivatives, and then we use the spatial derivatives to learn the time derivative, and then what we do is that we shift the stencil and shift it again. And so the idea of this doesn't mean that this doesn't mean that that convolutional neural networks are finite differences, but the same idea that underpins writing the evolution equation with finite differences also underpins convolutional neural networks. And so what we did back then is to use, if you want, convolutional neural networks in space and recurrent resonance in time in order to use spatiotemporal data and learn partial differential equations and then solve them. So again, the point of this is, well, okay, I mean, Petros is right. I did want to say that we were playing with some of this stuff back then, but the idea is that numerical algorithms that we know and love map to beautiful and useful architectures, and maybe it's worth mentioning, 2 years ago, I think, Nick Zabaras, who is a friend, has a nice paper in which he talks about how under some special conditions, transformers correspond, the evolution part in transformers corresponds to Adams-Bashforth methods. And also, I wanted to mention another chemical engineer, Dimitrios over there, who used neural network basis functions for solving partial differential equations. And then Paris is somewhere up there, and George Giannakis also. There is not just a rediscovery, this is building a much broader program on being able to use neural network techniques or machine learning techniques, if you want, to learn right-hand sides of equations and also learn solution operators. And since this morning, I put this while we had lunch, since this morning there was a discussion about discovering algorithms, I wanted to tell you that if in this neural network on the left that I showed you before, you hardwire all the black parts because you know Runge-Kutta, and you leave the right-hand side of the equation to be discovered from data, you can flip the colors. You can choose the equations you want to integrate, and then leave all the other connections, their existence and their parameters for free, and then you can discover Runge-Kuttas that are good for a particular problem. This is a problem that, as I was kind of saying in the morning, I'm thinking it more as a mixed integer nonlinear optimization problem. Looking at the time and what I wanted to tell you, let me skip the no parameters part and tell you about what I think is particularly fun, which is the no space and no time. You may have read the Greek version of what Giannakis said, αν δεν μπορούμε να αλλάξουμε την πραγματικότητα, ας αλλάξουμε τουλάχιστον τα μάτια με τα οποία τη βλέπουμε. Και η ιδέα εδώ, let me go back to English. The idea here is to say, so these are streamlines from an ABC flow. It's a steady flow, it has chaotic streamlines. The question is, how do we make a transformation in a latent space for which we don't have words, but in which the problem looks simple, okay? In which maybe we can flow box these and they can look like just nice parallel lines. Or just being playful, this is Dora Maar, who is one of Picasso's muses. This is how he painted her. It always makes me think that you're looking at her simultaneously from two sides. This is how Man Ray photographed her. It's clear that it's kind of, well, you have to know, but it's the same person. The idea is, how do we fuse information, which is another thing that came up today. How do we get different observations of the same thing and understand that it is the same thing? The important thing is, how do we take data and transform them into a space where it is easy to solve them? And in 2011, DARPA had what they called the Shredder Challenge. They took 5 documents, they shredded them into pieces, and then they gave $50,000 to whoever put them back together again. This is an easy task. I can do it now in 15 minutes. But it took a month before somebody claimed the prize. The basic idea is to use smoothness and data and then try and this is mathematics for solving puzzles. How do we take pieces and put them together in a meaningful way using smoothness? And here is the solution of a partial differential equation. It's a Ginzburg-Landau, it doesn't matter. Space and time, this is the printout as it comes out of the computer. The solution patterns are blue and green and whatever. And what you do is that you take these and you pass them through the shredder in the office and you get 512 trajectories. But now you've lost space because you mixed them up yourself. And what you do is that you take each one of these 512 time series and you do data mining and understand that it's a 1-parameter family of time series, and you order them based on this latent coordinate that you found from data mining. And lo and behold, what you get is something that's 1-to-1 with the original space. This is a problem where there existed nice space and we messed it up because of the way that we were observing. But more generally, the idea is, if you have disorganized data, how do you reorganize them in a space where the behavior is smooth so that you learn the model in the nice evolution space, whatever you consider nice to be. Here is a little example of this. This is 800 oscillators. This comes from work of Strogatz in the late 80s. They depend on both X and Y. They're phase and amplitude oscillators. You run them. And as you run them, what you see is that they very quickly organize themselves along a 1D curve, and then they keep the same order. You see the coloring that I did. I didn't tell you how I did it, but the coloring, if you observe, it kind of remains. The real good space in which you should be studying this problem is not two-dimensional space, but the arc length along the curve. So the idea is to study the behavior, analyze the behavior, find a good way to parameterize the behavior by looking at the behavior itself, and then learn the operator in the right space, in the convenient space, in the smooth space, in the beautiful space. And this is exactly the same example. And the main thing, and I hope this conveys it, if you look at what every point does when you just label them randomly, it looks like a mess of spaghetti. But if you order them, then you find a data-driven emergent space in which the behavior looks smooth so that you can go and learn the operator there. We use exactly the same tools as before, and we can learn then the partial differential equation along the arc length of the curve by discovering the arc length of the curve and then solving the problem in this space. And one of the things that may be worth mentioning, it's kind of cute, is you have an operator, but it came out of data-driven processes. So you don't really know what the operator is, and you also, then how do you know what boundary conditions should you use for an operator that you know as a black box? This is an interesting problem for which we have at least the beginnings of a solution, which is how in a data-driven way do you figure out if a problem is well posed? In effect, again, what I'm telling you is that I believe there is a lot of very interesting math problems. How do you figure out if a problem is well posed? What are the right boundary conditions for an operator? How do you discover an algorithm? There is problems that normally you don't do because you have a formula and you work with it. But if all of your information comes in terms of data, how do you decide these problems in a systematic way? This is a slightly less trivial example. It's 1,000 Hodgkin-Huxley neurons. They are coupled in a Chung-Lu network. It's a non-trivial thing. It has something to do with the suprachiasmatic nucleus. They are all synchronized together, so you have 800 limit cycles, you see, and because each of the neurons is a little different, each of the limit cycles is a little different. But if you analyze the behavior of these 1,000 neurons, you find that it's really a two-parameter family of behaviors. And therefore, if you don't plot the neurons by first, second, third, fourth, but you embed them as points in this emergent space that comes from observing what they do, then what you see, and you will see the stupid things we have fun with. We were so happy when we saw this first movie. If you look at the behavior of this network embedded in a right data-driven space, then it looks like a smoothly evolving field. And it is possible to find a much nicer, smoother, lower dimensional model by working in this representation rather than in the original random spaghetti representation from 1 to 1,024. I'm looking at the time and I really don't have almost any, so what I'm going to do is that I'm going to jump over some of the things that I wanted to tell you and tell you that one of the things that I believe is a very important item is to try and, what does it mean to find the right space? Among all possible invertible transformations of a problem, can we find one that is most representative? Can we find a normal form for the problem? This is a partial differential equation. It's called the Kuramoto-Sivashinsky. It's one space and time dimension. And the main idea of these 4 slides is that whether you sit at points in space and take short time series, or moments in time and take little neighborhoods, or take little patches of space-time, or even have traveling observers, it is possible to systematically analyze the data so that all of them will be embedded in the same latent space. So the idea is, if you have a symmetry group, like translational invariants, or scale invariants, or diffeomorphisms, how do you do gauge invariant data mining? How do you analyze the data so that you factor out all of these possible transformable to each other representations and choose one representative, decent one, in which you would like to work? And so I will kind of jump over some other stuff and finish with some pseudo-art. I used this slide a long time ago. The idea is that if you learn models in a data-driven way, it looks a little bit like a crystal ball. You ask a question, and you get an answer, and you don't really know what mechanistically went into the answer. We trust the algorithms that do the data processing, as opposed to trusting a physical understanding of the various terms that play a role. And what I wanted then to say is that this is horrible, the colors now, I apologize. This is Athens, so this is the Academy of Plato. I think it is Socrates and Plato. I'm told no, it is Plato and Aristotle. But the point is that in the Renaissance, people discovered perspective, the point at infinity, the projective plane, and took a lot of effort into representing things the way they look to you. And they took a lot of effort in order to do this carefully, okay? And when photography came, there just was not much of a point in making normal paintings anymore, so people started doing impressionism. How would you feel? Or what the Cathedral of Reims would look like in different weathers and different times of day. And my point is the following. This is the Vitruvian Man by Leonardo. Okay, so if you would like to make a model of something, you would like your model, we are used to having the model reproduce what we see. We would like the model to be a normal mirror. And usually we think of a model that is not so accurate as a slightly distorted mirror, and we have to fix the mirror in order to, we have to add some terms or add some physics in order to take the model back to look like the truth. What I want to rather talk about is a slightly different version of this, in which you may have, bear with me, you can have oscillations in fluids, oscillations in chemistry, and oscillations in lasers They all look different, but they are all realizations of the same normal form. And so the idea is not so much how to correct the model, but actually trying to find what is the correct universality class in which the model lies, so that you can take informations from lasers and chemistry and fluids and actually fuse them together. That's what this next slide is supposed to be. That as long as we know how to take something to the normal form representative of that universality class, then many different systems can help us become part of the same picture. And this, I didn't have sound, so you will kind of believe me that if I played this, it would be the 4-cembalo concerto of Bach, and if I played this, it would be the 4-violin concerto of Vivaldi, and if you heard them, you would say, it's the same thing. But it isn't. It is the same thing observed differently with different frequencies. And so the last thing that I will finish with, this idea of having different realizations of the same thing and how do we fuse them together and work with them, I think the most prototypical version of it is literature and translation. Jhumpa Lahiri, you may know her, she is a Pulitzer Prize winner. She wrote The Interpreter of Maladies and The Namesake, for those that come from Harvard and Boston. And then at some point, I think because of her Italian companion, husband, she decided to start writing in Italian. And she wrote, after some years, this book, in other words, in altre parole, that on the half page is the Italian text, and then on the other side is the English text translated by somebody else. And the point of this is, the point of the book is how difficult is it to write in a separate language, because idioms are so special in the one language, and then you need many, many, many words in order to describe them in the other. This is a sort of literary condition number. The transformation from one language to the other is very close to singular. And I read the book, and it's exquisite prose, and it basically goes on for pages and pages about how difficult it is to translate one language to the other. And so before I put the book down, I said maybe there is like a resume at the end. There is some sort of summary. And there is an afterword, and I read it, and I was just flabbergasted, okay? So, in 1939, 15 years before he died, Henri Matisse began to move away from traditional painting and develop a new artistic technique. He went from functions to pixels. He went from analytical solutions to data-driven ones. It involved cutting up pieces of paper that had been painted in gouache in various colors, pixels on the screen. Matisse then combined and arranged them, the different pieces, to make an image. He fixed the elements with pins, then with paste. He stopped using the easel, the canvas. His main tool became a pair of scissors rather than the brush. He used to call it painting with scissors. If you want an example of this, here is Matisse, and then this is Matisse painting with scissors. And this says, you see that he is sitting in a wheelchair. He says the method, a synthesis of collage and mosaic, arose out of certain limitations. In the same way that the reason that we go to data-driven modeling comes from limitations that we have in doing traditional math modeling. The eyesight of the 70-year-old painter had deteriorated. After a serious illness, he used a wheelchair. One day he was inspired to make a garden in the house, and he asked the graduate students to paint the paper and put it on the wall. So the last thing that I'm going to make you suffer through is this paragraph that says, for Matisse, cutting was not only a new technique, but a system for thinking about and expanding the possibilities of shape, color, and composition, a rethinking of his artistic strategy. The painter said the conditions of this journey are 100% different. He compared his method, which he called painting with scissors, to the experience of flying. And when I read it to Rafi Koifman that I told you about, he says, but we have a code that does that. Thank you.
Late.
Sorry.
It's been a busy day, but we have Ioannis, so plenty of time for questions.
I'm around.
Now, we can have some that people can say. Are there anybody who would like to ask a question?
The next person can come and set up.
Yeah.
Yes.
Yeah.
Are there any examples of applying this method to more complex fluid flows? Turbulent flows, something like that?
We are playing. There is a basic theorem that's called the
Maybe Ioannis So when we put this session together, we want to bring people from very different disciplines. That's why it was possible. But I think Giannakis spoiled this effort by putting literature at the end of his talk. So that brings naturally the next talk, which is about journalism and computational journalism, which is going to be given by Sotirakou. Katerina actually is going to be defending her PhD sometime next week. So I would leave it up to her to tell us what is this all about this new and exciting field of computational journalism. Katerina, thank you.
So, hello, I know I'm the last one, so I try to be punctual. So what I'm going to present here today is our work in the University of Athens at the Department of Communication and Mass Media Studies. What we are doing now is we are using artificial intelligence to solve a lot of problems we have in social sciences. So here you can see we have the computational journalism group in the Department of Communication and Media Studies, and what we are doing is we are mainly interested in solving problems in the journalism studies by using data science and computer science. And we have a lot of things that we're doing. We coordinate research projects on these areas, and with Python and machine learning to journalism students, both bachelor and master students. And I know it's maybe hard to imagine, but we actually teach Python to journalism students and machine learning, and they love it. So here I'm going to say some things about social science. So social science has started to move away from qualitative and quantitative methods and present a holistic analysis of data using modern computational tools and data-driven approaches. So data science allows social science to provide more accurate understanding of the underlying phenomena and to actually understand how people behave online. So computational social science has the potential to change social science research and provide a more effective approach of dealing with complicated societal challenges that threaten our democracies, such as disinformation, hate speech, inequality, and so on. There are many problems in social sciences that can be addressed with computational social science. Therefore, experts from all technical domains are needed to solve those problems. So the objectives and the research questions of my work, we actually focus on journalism, and some of the questions are: how can AI provide a nuanced understanding of what constitutes quality journalism in the digital age? Are subjectivity, emotionality, entertainment, and quality of language related to journalistic quality in online news? And what are the exact contribution of quality criteria? So we actually studied a lot of, journalism principles, news values, and other journalistic criteria of quality, and then we came up with a framework and some machine learning models to validate that. So those are some of our questions. I don't really have time to go through them all. I will show you today some studies that we've made, and the findings of these studies will result to some guidelines for journalists. So journalists would know how to write a news piece that is of high journalistic quality and resonates with their readers, and also can be used on various industry applications. So those tools utilize predictive models and can be useful for publishers by helping them to better understand how to reach their audience, and also for journalists to write better articles. This particular work has attracted funding from national and international bodies, and all of those models and the results will be implemented to an intelligent agent that will be developed in the end of this year in the Greek language. So a quick introduction about how we can use journalism and machine learning together. There are a lot of examples out there. There are some great examples of Quartz and ProPublica and also BuzzFeed. They use data journalism a lot, and with data journalism, which is, doing journalism with data, comes along also machine learning. So a lot of them has, like for example, let's take the Quartz example. They took 27 mass shootings and their coverage, and they used NLP and showed that when the mass shooter is white, then he's presented as a lone wolf, whereas when he's black or Muslim, all the race is presented as a mass murderer. So we have a lot of examples like this, like using NLP. We have the machine bias from ProPublica, where they reverse engineered some algorithms that are used in the states to forecast, let's say, the future criminal recidivism rates with white and black criminals, and they discovered that the algorithm is biased against black people. Those are some of the examples for journalism. I mean, like, we use all those tools for investigation, for our work, and then we have a lot of other tools that are actually for publishers. And this is how we can use the robotic reporter, as we say, which is like a robot who produces text or sound or anything. So we have robot journalism that has been introduced the last decade. This trend is driven by the need to maintain a competitive advantage in an ever-evolving news landscape, which is being shaped by, all this social media, technology giants, etc. And Bloomberg and Washington Post are pioneers in the field. So they are really into machine learning for writing reviews, for broadcasting, and a lot of other things. So now I will begin with our studies. Our first study, we used data from the blogging platform called Medium. So what we wanted to do is to create an algorithm that can actually predict the perceived quality of articles published on this blogging platform. So this research is one of the first in the area, and what we're trying to do is to see what is, how people react to an article, and what makes them perceive it as a quality article, let's say. So what we did, first to say what is perceived quality. So perceived quality is the customer's perception of the overall quality or superiority of the product or service. And what we're doing is, of course, although finding a news story interesting is a matter of personal taste, according to previous research in the field, it is possible to create a taxonomy of certain attributes of news that can actually influence audience engagement and use it for digital news stories. So we created this framework. This is based on news values and a lot of work from communication studies. The framework has 3 dimensions: author, content, and context features. So the user-related features, because it's a blogging platform, we have a lot of features about, the social network of the author, which is very, very crucial to his following and also to people perceiving something as quality, because you have an author who is established on the field. Second, we have the content-related features with 2 sub-dimensions. There we have the article length, the number of images, if the article has bullet points, if it has links. Links, for example, is a characteristic that shows transparency, that when you have external links, you quote something, or you have an external source, which is very important for journalism. We have the readability score. The novelty, for example, novelty is calculated using a 3-day sliding window, and then we see if the same words are, in the titles of news with the same topic, for example. We have other features, temporal and genre-related as well. So what we wanted is to have something of a measure. So here we got the claps. The claps is our dependent variable, and it's how many times the reader claps. They think it's of quality, or they think it's important. Previously, this claps button was not claps, was recommend. So would you recommend this article to somebody else? And the claps is the same. So we think that is a good measurement for perceived quality. Then we scraped the Medium platform. We got a lot of data from September 2017 to September 2018. Here you can also see the categories that we chose. We chose 6 different categories, and we did 2 different phases of experiments. First, we used all the data, and then we used all the categories separately to find different results. So here we can see the feature importance of our features, and for the interpretation of our best predictor, which was the random forest. Here we see the contribution of every feature to the prediction. And here, of course, and we will see it later as well, we have the social network of the author as the best predictor, and then the article length and the number of images. Here it's the different categories, and you can see at the bottom the different genres of news. And again, social network is the first, not only how many people follow the author, but how many people the author follows is also important for this prediction. Then we have the length. The length also shows if an article explains a topic in detail or not, which is important also for investigations. And then we have the images. The images and the number of images that exist in an article is a very good predictor. We have a lot of differences as well. The readability score was only associated with business articles, subjectivity and tone to business and technology. The bullet points were quite significant for technology, that makes sense, I think, and lifestyle. And the temporal factor hour was only a little bit important for lifestyle dataset. So we really thought that day or hour would be a good predictor, but it wasn't. So now we're moving on to the second one. Here we are actually trying to predict the quality of news articles, not blogs anymore. We are going to examine news. So the question of quality has been discussed a lot in our departments, and all of the communication scholars are talking about journalistic principles, news values, impartiality as the cornerstone of journalism, and so on. And what we did was we tried to move away from all those content analysis that social sciences, mainly do, and go beyond that and try to solve this question using computational methods. So at first, we interviewed 20 professional journalists and academics, along with all the literature reviews that we did, and we came up with a lot of journalistic principles, and we designed a framework. The framework looks like this. So those were the principles that we could code somehow, that we can operationalize as features. So the first dimension is impartiality with subjectivity in news stories being calculated with a subjectivity lexicon, self-disclosure that measures self-reflective pronouns. Then we have the dimension of information quality that has the diversity of sources. How many sources do you have in a news article? How easy it is to read, if it's long or it's small. The language of news, it's about how many adjectives they use, because, for example, the New York Times, they don't use any adjectives, while Daily Mail uses a lot of adjectives. This is something that also shows the quality of some of the text. We have the numbers, the capital letters in the story. Then we have the entertainment dimension. And here we have, we created some lexicons with sensual words, with animal names, with crime and conflict words. And for the celebrities, we took all the celebrities, all the popular people that appeared in the Time magazine at the 100 people of the year. So we took 15 years of all the magazines. So we created a list with popular people, let's say. And finally, we have emotionality. Emotionality, everybody knows about that, and we calculated the emotions of the title and the emotions of the text. So for the corpus here, we used annotation. So we took a random sample of 2,000 articles from 15 newspapers, both, highbrow newspapers like The Guardian and tabloids like the Daily Mirror. And then we used a lot of different models to see if our framework actually works. And it seems that it works. So we used the L5 package to see the importances, and I will show you here the feature importances. So the first characteristic of a news article is difficulty, how easy or difficult it is to read, right? Then we have the length, which makes sense because the high-quality articles are basically, over than 600 words. We have self-disclosure, which is something that we didn't expect. We have the diversity of sources, which should be in there, and it is. Adjectives, numbers, headline words, trust, and joy intensity. But this is not enough for us, because our main reason for using supervised learning was to be able to explain the results of those algorithms. So then we tried to explain the decision trees, and since the best model was the XGBoost classifier, here you can see the results of a single tree of this classifier. And this is a visualization of this tree. The histograms depict each variable's feature space distribution. The y-axis is the sum of the samples from the two categories that are stacked together, while the node size is in proportion to the total number of samples in each leaf. So leading toward the bottom, the nodes become purer as the decision splits create finer regions until the samples are completely separated into buckets. So what we did, we took the four main pies, as you can see over there, and tried to analyze them. So we saw all the rules and wrote down all the numbers. And we have two main rules for a good article, right? So a high-quality article based on this tree is longer than 558 words. It is not very easy to read. Its headline includes no more than 24 words and cites at least two named sources in the story. According to the second rule from this tree, if a news story is less than 558 words, it's fairly difficult to read, includes less than 20% words expressing joy, and has a minimum length of 256 words, might also fall into the high quality category. So we have one rule for long articles and one rule for short articles. Here you can see a visualization of a random high quality article and a random low quality article with a good probability. And we can see here the dimensions of our model and how different the articles actually are. So what we want in the end is to have this model implemented in an intelligent agent used from journalists, and when they write the article, they can see these recommendations, let's say, and be able to write better journalism, which is crucial for our field. So here we have some conclusions, but I have already, discussed most of them, I think. Yeah, entertainment is not present in the top quality predictors. That wasn't expected. We actually expected that entertainment would be one of the top 5 predictors because, all the tabloids use a lot of words about crime and stuff like this, but it wasn't. The language quality actually monopolized the prediction, and this makes sense, and the literature also supports these findings. The third study is all about engagement, because now we have a competitive market. The landscape of news is very antagonistic, and everybody wants their stories to be popular. So here we have, of course, some theory behind it, a theory from communication studies, from marketing studies, from advertisement studies, and we can see that we have now the like economies. So a news article, even for the New York Times, is good if it has a lot of engagement on social media. And that is something that also alters the way that journalists do their work, because a lot of times they don't, report on a story unless it's trending on Twitter. So we have a lot of examples like this. And our goal was to find how we can have an article that is of good quality but also engaging. So here we used a different data set, a total of 113,000 stories, and we also downloaded data from the same stories from the CrowdTangle platform from Meta, and we combined those together. We matched the headline or the URL and had a very big data set with all the features that we used before in the previous study and all the engagement features, let's say, all the likes and shares and comments on Facebook. So here we can see the permutation importance for the top 10 features, so we can see that, that how many words exist on the title is a very good predictor. This is also something that I will show later about fake news. Fake news also can be predicted with title words. Because if you think about it, fake news have a lot of things packed into the title. They explain the whole thing into the title, and a lot of times, if we can measure the cosine similarity, between the title and the text, they don't really match. So they say a lot of things for clickbait titles, and then nothing of importance in the actual text. So here we can see the difficulty. The number of celebrities is something that came up here for engagement. We have also the subjectivity expressed in the headline, which is something that came up, and the feeling of arousal is present across all the different engagement measures. So the first model tried to predict comments, the second shares, and the best one was the one that predicted likes. Here we have again the explanation of a tree, and we have some rules. So here the rules are for engagement. So according to the machine learning algorithm which predicted the total interactions on Facebook, so here it's not about likes or shares or comments, is for the total interactions, okay? So the total number of engagement, let's say. So if a news story has more than 595 words, it's comprehensible, has a long headline, cites more than 5 name entities in the text, and evokes to the readers the feeling of control over their emotions, this is arousal that we saw earlier, has a high probability of becoming engaging. This is for long articles, as we can see. We have a second rule for shorter articles. The headline must be even longer to have better chances for achieving high engagement. So the only thing that's different for short articles is the big headline. Our conclusions here, is again that information quality, which is language quality, I'm sorry, it's not information quality here, it's language quality, was again the most significant. And then we have the entertainment dimension presented here as a good predictor. Emotionality dimension wasn't so good for predicting engagement, but anticipation and dominance. Dominance is your feeling of control of your own emotions. Arousal is if you are angry. So it was my mistake earlier. So study 4, the impact of images on news quality and engagement. So here we try to see if we can predict the quality or engagement of the articles using the images. And we used mostly Amazon recognition for that. We used the same framework this framework, I don't know if you could see it, but this is the features are those things there, right? If we have colors, and what colors do we have? If we have animals, how many pictures are in the story and stuff like this. So this is our framework that derived from advertisement, marketing, and communication studies. Here you can see our accuracy. We only have 68 accuracy with just images, and then we can see that, of course, text is better. But when combined, they're not really much better. They're actually not even better, let's say. It's a good thing that images can predict quality and engagement, so we are going towards a good direction, but it's very hard to just use images to predict these things. So here we have the quality prediction with having a dolphin, a happy dolphin makes it engagement. Then we have fear, smile, food, etc. And here we have the engagement, which is totally different. The number of images is the best, and then dominant color, and so on. I don't have much time to go through the fake news study, but the results were like, if you have all caps in the title, and if you can use Facebook to predict something is fake, you have very, very good accuracy. So if you have likes of a story, you get 98%. So there is no excuse for Facebook, saying that they cannot control fake news. They actually can control fake news, and this is the proof. So to finish up, this is what we're building now. We got the funding from the European Union, and in Greece it's Revnokenotamo, the name. We got 1 million for that, and we're actually building the same models in Greek language, which is very, very hard. And this is a prototype of the system. This will be an intelligent agent where the journalists would write their text, and in the corner they can actually see the dimensions that I've shown earlier. So you have language, quality, subjectivity, emotionality, and entertainment. We have all the sub-dimensions there. So when they write something, the recommendation, for example, would be, you have a lot of anger expressed in your story, maybe, use some other wordings, or you need to use more images, or change your images, or, cite more sources and stuff like this. So this agent will be available on the end of this year, and it will be in Greek, and we have 11 million Greek news stories from a lot of different categories and from all the news outlets in Greece. So we're very, happy about this project. Thank you.
Thank you very much, Katerina. Any questions? Yeah.
Maybe I missed something.
Maybe I'm talking too fast, so it's...
I'm wondering about the quality metrics. Can you elaborate on that?
Yeah. So at first we did, we read all the journalism studies about that, transparency, impartiality, a lot of principles came up. Then we did a study where we interviewed 20 professionals, 16 professional journalists and 4 professors in journalism and communication. And yes, 20 experts in journalism. And then we got all their answers, and we created a framework based on those answers. And the only thing that we couldn't code, was the transparency and also the truthfulness of the news story, because we couldn't code that as a feature for Python, But all the other things, for example, to quote a lot of different sources, or to have a balanced news story, how many words are said about Mitsotakis and how many words are used for Tsipras, for example. This kind of things. Also, they said about, using sensual words or using a lot of emotion. They said that a quality news story shouldn't have any emotions and should be very, let's say, objective. But how can you measure objective? We couldn't measure objectivity, but we could measure subjectivity. So that's what we did. We measured for subjectivity. There are some lexicons out there, annotated lexicons from social sciences that we could use, and we saw that subjectivity came up in a lot of the studies, right? So yeah, we took a lot of principles from journalism, a lot of things that only exist in theory, like news values. For example, crime and conflict is a news value. We made a lexicon of all these words and applied it as a feature. So we tried to operationalize all the theoretical stuff that we could, that derived from theory and from our interviews with the experts, and try to do this with supervised machine learning. We tried a little bit unsupervised learning, but we couldn't explain the results. So we just, used it as a baseline, because it actually predicts very well if something is, engaging or not, but you don't know how it, decided that way. So we used supervised learning, so we know what we're doing, and we know that, for example, diversity is something that is important here, and is also important theory, and is also important for journalists. Journalists in 20 to 23, right? Not journalists from 20 years ago, like in the theory. So yeah, that's what we try to do. We have a lot of problems like disinformation or hate speech or polarization and other things in social science that we're trying to solve. And computational social science is rather new. And we really need, your input on that and your feedback on the things we're doing. Thank you.
Okay. Well, I'd like us all to thank Katerina.
Thank you.
And also I'd like to thank all the speakers of not only of the session, but of the whole day. And also I would like to thank all of you for your endurance and for your interest. We hope to see many of you also here tomorrow for the closing symposium of the HIAS. Thank you very much.